It's the same in regards to the final component. You're not actually making that component, you're making a tool to make that component with. So
it's funny how the march of progress is quite slow, because I guess maybe 30 years ago you'd get people saying, I can computer programming that, I can.
Welcome everybody to the MTDCNC podcast. I'm Lindsay Vickers and I'm your host for today, and I'm a proud member of the MTDCNC team. We've got 4 of us chatting to you today, and it's quite an exciting podcast. But basically today's podcast is all about exploring the importance of automation in the manufacturing industry, but not automation in terms of hardware. We're talking about software and making your processes way more efficient. We all know it's common knowledge now that automating your process is literally the key to survival in this industry. And with what we've just been through and the skill shortages in industry at the moment, we now know that we need to work on making all of our processes more efficient. But we always think of robots in this area, but today isn't about that. It is about the software. So it's not just myself with you. Of course, we've got the lovely Rowan here. So welcome to today's
thank you very much. That's the best way I've ever been introduced in my life, I think. That's lovely. Thank you.
Lovely Rowan.
Lovely Rowan, yeah. That's
well,
fantastic.
I wouldn't say anything horrible about you, Rowan.
No, of course not. No.
He's a lovely
Not
chap.
on microphone anyway. Not live.
So Rowan's looking after us. So Rowan, can you just give us a little bit of a background into who you are with MTDCNC?
Yeah, so I'm presenter at MTDCNC. We go around workshops. We're lucky enough to go around workshops around the UK, sometimes Europe, sometimes the world, and go talk to manufacturers about why they've bought certain machine tools, certain pieces of software, certain products, and find out exactly what problems they were facing and how they've solved them. And normally we get some lovely success stories. So we're going to be talking about hopefully how Hexagon
Manufacturing Intelligence
can offer again great products to help UK manufacturers and abroad win projects, win customers, and hopefully have some great success stories. But this is all, like you say, it's not about robots. This is automation, but it's kind of like workflow automation. It's software automation, which to me is kind of like the first stage in making a product. Is you need to program the machine, you need to set the tools up, you need to make sure all the simulations are correct, and then you can finally make the part and probably inspect it and then send it out the door. So I think that's kind of the framing of hopefully of what we're going to be talking about today.
Absolutely. Now that's Rowan's introduction. Well done there, Rowan. And next up we've got Paul. Paul, what's your surname again? Smithson. I couldn't even write it down on my piece of paper. So Paul, can you introduce yourself and tell me what your role is with Hexagon Manufacturing Intelligence?
Okay, my name's Paul Smithson. I work as a Visi support and services manager. My background, I started in engineering as a injection tool designer. I've worked at a number of manufacturing facilities, really, not just in injection molding, but die casting as well. So a varied industry knowledge, really, in the tool and die industry. But now, for the last 17 years, I've sort of crossed the line from the manufacturing or the physical manufacturing side to the more virtual side within the software. So using Visi to on the support and services. So basically supporting our customers to get the most from the products that we provide.
Absolutely. Okay, thank you for that, Paul. Got lots of questions to throw at you momentarily. And Gareth as well, the final person on the panel today, Gareth Henwood, whom of which I actually saw you out and about yesterday, didn't I, Gareth?
You did, Lindsay. So it's about, and I also saw Geo twice this week as well. So
I mean,
quite regular.
He gets everywhere, that man, doesn't he?
He does. But Gareth, introduce yourself, please.
Yeah, so my name's Gareth Henwood. I'm one of the area sales managers for Hexagon Production Software. I look after the metal cutting cam products and G-code verification and simulation software, and also our MRP solutions.
Right, thank you for that, Gareth. Okay, we're going to cover lots of topics from Hexagon Manufacturing Intelligence today, and we're going to be covering general machining, plastics, tools and die industry, complex machining, multi-spindle machines and how they can help your business. But let's start with the plastics, tool and die industry. Now, Paul, what kind of hurdles are you seeing in the industry at the moment?
So a common issue that we see quite a lot from the tool and die sector really is designers design components to supply us a purpose, but then they're not necessarily, or the components that are designed or an assembly that's designed isn't necessarily fit for manufacture. So we often have to take in components from other systems. So, we can't be proud over where the data comes from. So we have to import and work with that data straight out the box. So whether it's good data, bad data, we can't, or our customers don't like throwing that back to their customers and asking for more data or different data. So we have a range of tools really just to make that data good, valid, and then we can move on to investigate on how manufacturable it is. So for injection molding, that could be wall thickness, it could be draft angles, and a lot of plastic components, especially the bigger, more complicated assemblies, have lots of clips and things that need to be demolded to get the component out of the mold tool. And all this needs to be done automatically. So we have a range of tools to test mechanical movement. We also are able to actually investigate the injection of the plastic into the mold tool to see if you're actually going to be able to fully produce a working component. On the press side, again, sheet metal, stamping tools. There's a lot of fancy materials around, complicated materials, and they all have different characteristics when they're produced. So being able to have a range of simulation tools to be able to simulate that is obviously a benefit for our customers.
So what are the main problems then that people are coming to you with? Give us an example.
Well, basically, our customers, on the most part, are producing other people's components. There's only a small percentage, I would say, which are OEM manufacturers. So they never really know what they're going to get. So sometimes the parts that they're being asked to produce are within their comfort zone, and they can produce those all day long. They have the experience. But quite often, they don't. Who wants to turn work away? No one really wants to turn work away. So no one likes to say no. I mean, we're all engineers. We like to think that we can provide solutions to any problem that gets thrown at us. So so we have a range of tools to really aid us and support our customers in producing parts that may fall outside their comfort zone and their knowledge base.
And you have talked about, there's a lot of topics you've covered there already, Paul.
Yeah.
Let's dig into the first one. You mentioned kind of data and getting data from a customer's customer. And that is, to ground it, that's kind of model, that's 3D model data, right? Yeah, that's like a 3D model. And what kind of problems will people be getting when they get models chucked over them, maybe via email or by some file sharing service? What problems would they have trying to inspect that piece of 3D model?
Well, basically all a CAD model is a big mathematical model. So basically if the surface or solid data is not valid, so it's not mathematically valid, our functions within the product then may have difficulty performing as we would like them to. So the first step of any project really is to make sure that the data that we've been provided is in a good condition, especially with more complicated mold tools where there may be multiple impressions. You're going to make multiple copies of that data. So if that data is poor to start with and you don't go through the effort of running the tools to validate and get a good set of data, you then duplicate that. So you're duplicating the problem and you're just making a bigger headache for yourself.
And how easy are these tools to use? I mean, did the design engineers need to understand kind of U and V values on the surface and the surface normals and all these kind of complicated things to do with a 3D surface?
That would have been the case a number of years ago. Yeah, you are talking sort of those days are gone, luckily. I definitely don't look at parts like that anymore. So no, it is a process. I don't like to say it's automated because that would be, it's semi-automated, I would say. It definitely guides you down a line. It highlights where the problems are. And then there are a a range of tools to try and remedy those problems then. So, and we go, and even the solution is a process, because sometimes the first tool you use resolves a problem. When it does, great. I mean, we've got automatic tools to repair these models as they come in. But, you know, if it repairs 50% of the problems within the part, that's great. That's 50% I haven't physically got to interact with. So, but chances are there will still be one or two things to manually go and interact with. And then we have a range of tools. So the first, we'd try the one that would give us the most chances of success and sort of work our way through the line until we get a valid component at the end.
And do you think it's worth maybe trying to explain to the viewers, maybe some of those who don't know what goes, so general subcontract machinists may not know actually what goes into a mold and die kind of setup to make even what look like simple plastic parts?
Well, how long is a piece of string, really? It really does depend upon so many factors. It depends upon the equipment that they have to manufacture the tooling and manufacture the parts. It also really is impacted these days, I would say, on how much knowledge they have within their own industry. We've definitely seen a brain drain, if you like, of skilled engineers leaving the industry because they're retiring out of the industry, and they've gained so much knowledge over a lifetime, really, of working in an industry, and that is being lost. And we're trying to produce tools using and utilizing our knowledge and their experience, and produce tools that sort of provide that information to new users that don't have that experience.
And we all know that there is a big skills gap, and it's almost like your way of kind of working with what you've got now. And hopefully you've got more and more of these new engineers coming through, but doing that in a virtual world.
Yeah, we have a range of tools really that are more visual, so that they have a visual interface for new users that don't want to or haven't got the history of clawing through reams of data. So the way we present our feedback in a virtual environment is quite an important thing. It keeps the user more engaged and more inclined to use the tools in the future as well.
And moving on to going from kind of plastics injection molding to stamping it's quite a similar component. You're making the mold or the progressive die, but rather than filling it with plastic, it needs to be at high pressure. Instead, you're kind of stamping with a high force. Are they similar kind of products?
It's the same in theory, but it's completely different, if I'm honest.
Okay, that makes it easy.
We like that.
Yeah, brilliant.
It's the same in regards to the final component. You're not actually making that component. You're making a tool to make that component with. So you're basically ripping or pulling apart a component that's been designed for a purpose, and then you're using those individual parts to then make an automated tooling to produce that part. So on the most part, if the design of the component allows it, it will be automated. And again, if the economics of producing it is viable, because obviously to make something automated is more expensive to do.
And this is the manufacturing automation. Now, this is really high volume stamped parts, can be in the hundreds of thousands a day. Yeah,
exactly. So if the economics allow it, the investment will be put into producing a more automated tooling, but they can be semi-automatic. They could have a manual interaction with it. If small production numbers require it, they may be an element where there may be human intervention, so a much cheaper solution, but for much lower number parts. But basically, you're always taking a component and pulling it apart to be able to produce something else from it.
Absolutely. And you mentioned there's exotic materials, work hard, and new materials that are kind of more automotive. How do you see that trend? Is that going to be increasing? People are going to be looking at more difficult to stamp materials because of their mechanical properties?
I mean, this is viable for both, for any tooling really, or for injection molding and press parts. Material manufacturers are always coming up with new solutions, new materials they're never sitting on their laurels and just producing the same material again and again. They're always adding new additives to try and create more mechanical strength, or so that side of the business never stops.
And they're probably never thinking about the manufacturability.
Yeah, there is that, but you don't know how these materials are going to perform. So to be able to simulate or do an element of simulation to see how it will perform, or how it will provide a stable component dimensionally, is an important thing for our customers.
And how easy is a simulation to perform in the software? Because I know personally I've used kind of ANSYS and FEA software. It can be really quite complicated just to do kind of quite simple simulations.
It depends on which sort of simulation. If for injection molding simulation, you need to be able to put in some viable data to get viable results. For the press side, it's a lot more automated. I've got to say, you're basically taking a flat piece of material and then you're telling it its final shape, and the system pretty much highlights any damage that will be formed through the manufacturing process to get to that final part.
There's quite a few topics that we're going to cover today. Actually, we're going to cover, because there's a lot of products that you offer to industry, and we are going to cover complex machining. We're talking about multi-spindle work as well in industry. But let's talk about the general machining now. From yourself, Gareth, what industry hurdles are you coming up against?
So again, we're coming up against, or all manufacturers seem to be coming up against price. The material costs are rising. It's a very competitive market out there, and again, as Paul touched on earlier, the skill shortage as well. We're finding a lot of the experience, as Paul said, people are retiring, they're moving into different industries. It's good to see that there is now starting to become a big push on apprenticeships. Yeah. Which is great news, but obviously we're trying to help that process at the moment. So
there's always going to be a bit of a delay there as well, isn't it? That is happening, but right now, what people need, time is of the essence as well.
Yeah, no, definitely. They need to make these parts quickly and as efficiently as possible. So within EdgeCam, as many of our other solutions as well, we have a lot of feature-based recognition. So again, you can take in a CAD model, it will look for profiles, pockets, flat faces, holes. It'll bring in tap data. So again, it's doing some of the work for you. We can then, with these features, once you've set up the tooling database, which you can get EdgeCam to actually give you a suggested order of manufacture. If you want to go with that, you can. Just press a button and it will program it. Otherwise, you as the engineer, you can still say, oh no, I want to move the features up and down. So you've still got full control over it, but it's just speeding your process to get to that area.
And that's probably the job of the design engineer, who'd be sat in the office and they might have a big backlog of 15 parts they've got to program, whereas you might have 15 machines and 15 operators who might be sat there idle because they're waiting for one design engineer, because companies are struggling to find those skills. So do you find trying to reduce the workload of that design engineer is actually quite a successful approach? Yeah,
definitely. And as you've touched on it there, when a spindle's not running, the company's not making
That's
money.
very important, is that spindles need to keep cutting metal.
And that's the idea with our solutions. We want to be programming offline, proving out the process, and again, linking it with, we've got another product, NC Simulard G-code verification and simulation software. So you can validate the G-code, make sure there's no collisions, and you can actually measure the part digitally rather than on the machine. As soon as the process is fine, G-code in, press the button and walk away.
As long as those tools are set right.
Yeah, again, there is that element from that. But again, it's speeding up the process. You're not having to, it's doing away with the conventional prove out where when I was running machines, you'd create a program that you'd sort of like single block it through, you'd wind the speeds up and down. So again, you're actually taking that process away and being more productive.
Are people nervous about this? Because of course people will, we are human, we are often set in our ways, but is there a nervous thing in the industry where people they want to prove it out, they want to see it physically done, or is it just a natural progression for people are people nervous taking on this virtual world into their machine shop?
Not nervous. It provides confidence. That's what you want to do. You don't want to be sat watching a machine running. You want to, and it can run for many hours. So you want to be able to press the button and be confident that your part is going to be to spec at the end of the manufacturing run. So it's to be able to simulate it virtually. You can try out different manufacturing techniques even to get to a finished working solution.
And are you feeling that people are free to embrace this? Like, what are you coming up? Because I love success stories. I like to talk about all of this, but let's get to the real life side of it. How are people taking on board all of this in the real world?
So again, it's, as you say, some people are nervous because they think it's going to take away their job, but we need to educate them on some of the strategies that our solutions offer. Like the waveform technology that it's been in EdgeCam probably for the last 12 years. We developed that from the milling side, and that's really made a difference in cut down roughing cycle times. So again, it's trying to educate to that user that's nervous that there's no way you could manually program this, so you need to adopt some of the modern strategies and technologies using the latest cutter technologies as well. So it's sort of like working with them to give them some tools to say, yes, you're still in charge of doing that part of the process, but giving them some new modern methods of actually producing the parts faster.
It's funny how the march of progress is quite slow, because I guess maybe 30 years ago you'd get people saying, I don't want a computer programming that. I can sit down, if I've got this weird curved surface in this mold. I remember someone telling me they on a Heidenhain control, they had this weird surface. They figured out some really strange mathematical way of hand programming this whole complex surface and measuring it with some drop line and some sine bar. God knows how they did it. And now CAM is, in my mind, it's fairly ubiquitous. I mean, we're going to touch on sliding heads, where in the industry they maybe not have taken on CAM as much as other industries. So we're going to discuss why maybe they could do. But it takes a long time for these concepts to sink in that actually this might be a new best practice. It's not now, but it might be in 10 years. So if you want to be ahead of the curve, you need to start adopting these practices. But if I could play devil's advocate here, and you're talking about making a part, checking it before you even run it. Now, I can imagine there's some engineers who are listening to this, some people who run machine shops who go, well, hang on, Gareth. I have no idea until my part is correct, until I've run it on my machine. Whether your software says it's right or not, I don't know until I've got a good part out the door with a green sticker on it, or however they say that it's passed inspection. How would you respond to that devil's advocate?
Yeah, again, there's always a doubt, because you need to prove the technology to these, customers, the users. So again, it's through experience. Again, when we're validating it, if we're using NC Simul for instance, we will come in, we will take a download of your control on your machine. We use the actual parameters from the machine. We'll take the macros out of it, and use a subroutine. So we'll take that technology from your actual physical machine, build that into a digital twin, and then sort of basically we've got your machine on a PC. So it could be on your desktop, your laptop. So basically you're going to crash pixels rather than spindles.
That sounds like that's a good tagline. I like that.
I really like that.
Pixels are a bit cheaper than spindles, aren't they?
Yeah, just a tad.
Definitely.
Can I jump in again? Where do you see the role of, let's imagine the machine shop again, you've got 10 operators, 10 machines, let's say one design engineer in the office. Where do you see the role of what would originally be kind of classed as a setter operator, which originally would not be hand programming, they may just be setting up the jobs and pressing go. With the advent of, I guess you get younger setter operators, they may be coming from school, age 16, doing the apprenticeship. Do you see those kinds of people as your kind of your new customer base who could be using the CAD/CAM software on the shop floor and programming their own jobs? Do you see a movement from the design office to the shop floor? I mean, what kind of trend do you see with the adoption of CAD/CAM?
Again, a lot of my customers generally are programming on the shop floor. So it would be the setter operators. There are companies that are lucky enough to have standalone programmers. So again, with the young generation now, they're so always on their phones and they're very IT literate from that side. So we've put steps in our software to make it very easy to a user experience. So there's a 5-step process. Pick on Hexagon, for instance. You literally load the model, search for features, apply a toolpath, simulate it, and output the G code. So again, we're trying to make it a logical step. And again, the same with NC Simul. Load the G code, simulate it for collisions, validate the part by measuring it. So we're trying to make it an easier learning curve to bring the young generation up to speed.
Do you think, again, I'm going to play devil's advocate, so very sorry about this, Gareth, I'm putting you on the spot here again. Do you think that maybe there are some dangers if you did approach it from a perspective of, look, we've got 8 setter operators that are between 16 and 25, look, they're on TikTok all day, they're liking each other's posts, they can definitely use some cam, surely they can cut metal, right? Do you think there is definitely still a case to be made for experienced engineers and some kind of mentorship to make sure that those younger people who might be proficient at making a good-looking program, maybe not proficient at yet making a program that can make a good part?
Yeah, there's definitely, you're never going to beat the experience because, again, myself and Paul, we did our apprenticeship the old school way, so we were winding handles. You gain the feel of the machine, the vibration.
The old school way sounds like a lot of made cups of tea.
Not that often.
Oh, controversial, controversial.
You always got that experience, and again, normally with apprenticeships, you'd have the older engineers, they would be mentoring the younger engineers, and it's good. We're doing quite a bit with colleges locally, the engineering colleges now, and when I go in and I'm offering our solutions, it's great to see that a lot of them have actually got a section of manual machines, so they are teaching the old school ways of actually winding handles, so at least the youngsters now are getting a proper feel of what's going to happen if I push that too hard or not, whereas by just doing it on a computer, it's going to crash it on there, but you don't necessarily have the experience from the manufacturing side.
So let's just move on now. So to yourself again, Gareth, sorry. You chatted a lot. We'll come over to you again, Paul, in a moment. But why doesn't the sliding head market, we'll move into that because, Rowan, you mentioned it, mainly use CAM then?
So again, historically, due to the sliding head and multi-spindle machines, there's so many axes to control, so they're very difficult to get CAM systems to operate. Hexagon saw this as part of a gap in our market. So in the middle of lockdown, we suddenly got an email the next day, we've gone out and bought a spree for an American CAM product from DP Technologies. And basically it's the world's leading sliding head CAD-CAM software. So again, that's a great addition to our portfolio, and that was the one area where we had a gap. So now we've got a spree, which is a fantastic product. It allows you to again program it using the CAM side of it, but again you can fully simulate what your machine's going to do, so you've got all these axes moving, whereas historically customers have been programming it on machine, so then they still have to prove it out because they don't want to make sure that the tools are missing and colliding, whereas you can do that all in the spree. Does all your weight codes, your synchronization, and you can reduce the cycle time because, again, sliding heads and multi-spindles, you're making big batch parts.
These are high volume. It's
High
not quite stamping,
parts.
is it? But it's
No.
pretty high volume.
So again, on a batch 50,000, 100,000, every second that you can knock out of that makes a big, big difference.
And exactly move on. That's exactly the question I was going to ask. Is some people might argue, don't you think, that maybe programming by hand, they can really tweak those programs and try and shave off every little bit a second, whereas the CAM systems that I've used personally will generally spit out a good program that will make a good part, but there will be little areas of optimization that you could do if you were hand programming. So
When just really quickly, when I went over to one of the shows in Germany a while ago, we met some of the guys on a spree, and this man was absolute genius, but he talked a lot about AI, and I don't know if we kind of delving into a very, you know, a big area. But that's, you know, if he's talking about AI with his products, it's all about, like, our brains can't compute with a lot of this. This is what these systems are all about. Like, the human, as good as we are, and we have that feeling of needing to stay in control and being on top of these systems are just on another scale, aren't they, really? They can compute in a way that we can't.
Yeah, no, definitely. And there is AI in Esprit, again, going back to the feature-based recognition. So you can load in the part, and again, it can have, you know, so many different accesses, but it will pick out all of those features. So again, that's done a lot of the work for you, and then you can apply, go into the top end of Esprit. We have a knowledge base module, which again, basically you teach it, and again, once you've fully taught it, again, your speeds and feeds, your preferred methods for materials and things like that, creates a template. So again, you can literally bring in another part, and you can just pull a template from the knowledge base, and it programs it just like that. So again, this is automating the process, but it's still keeping your spindles running. Whereas if the guys conventionally were doing it on the control, proving it out, you're not making money. So again, it's a great bit of technology in Esprit that's, again, we're just developing, so it's just going to get better and better.
So does that require your design engineer to input kind of how the company, as a general kind of best practice, would machine a certain feature or a certain pocket or a certain part?
So again, yeah, generally, obviously the sliding head operator is very skilled in their field, so they've got a feel for what works on the machine, going back to the old hands-on approach. So again, they're just feeding that data back to these knowledge-based templates. And again, they're being saved, and then when they're doing that feature or they're using this specific material, it just pulls in all the data for them, which is based on proven data from the shop floor.
That is fascinating. And one thing I find really hard to get my head around is the sliding head configuration as a whole. Generally, you kind of have a lot of different platens, and it feeds to another to the other spindle side, and you've got kind of loads of B axes, and you look at a Star or a Citizen or any of the sliding head machinery, and they've got so much tech packed into a tiny space. And this is probably a bit of a technical question here, but how do you find the struggle between to develop the processes to handle every single different kind of axis? I mean, can Esprit really handle a 9-axis or 10-axis sliding head machine?
Yeah, no, again, Esprit's been around probably 30 years. You know, they've built the technology up over the last 30 years and really aimed it at sliding head, multi-spindle. So again, we have dedicated teams in the US, in Europe, for creating these post-processes. And again, a lot of these post-processes, digital twins, they are certified by the manufacturers. You know, we've got some big global partnerships with the likes of Star, Citizen, Tornos, you know, the big sliding head manufacturers, DMG as well. There's global agreements with these companies. So they're proven by the engineers and the companies themselves as well.
I think it's fascinating how complicated these pieces of software can, or sophisticated. They're not just complicated for the sake of it, especially when they can handle such complex machinery as sliding heads. But I think we can move on to kind of the simulation side. We've already talked about NC Simul quite a lot, but for engineers who are not necessarily design engineers, who've not used FEA, not used CFD, they don't do really hard, rigorous design, but they do manufacturing. So they'd be making parts, making plastic parts, making stamped parts. Where do you see the use of simulation? Do you think that's going to be used a little bit more if rather than having to, for example, in sliding heads, make a part, measure it, make a part, measure it. Instead, you'll be simulating the program. Or if you're stamping a part, would people be stamping a part, measure it, make sure it's right? Because there's a lot of kind of trial and error that you get in manufacturing as a whole.
I mean, simulation is within all our products, in all aspects, whether it's the manufacture of the parts for cutting tools and material removal or bending of components. So we don't try and have simulation at the end of the design process. It's to aid the design process. So we try and slip in tools to simulate every part of the development of any design.
And how would you convince an operator, so setter, someone who we've discussed who might be on the shop floor but not a design engineer, that maybe they should be looking at trying to use simulation to reduce their workload, looking at automation, looking at all these solutions that we've talked about today?
A lot of the time, the products talk for themselves. Really, it's a case of getting people in front of them, and what I find the most successful is getting an engineer to open up about the problems they've got, admit to it. A lot of people, they've got solutions, but they may not be the best solutions. So what I often find is if I can get an engineer, or if I can show a new prospective engineer some areas of the product where I've got a good feeling, where from my experience that they've, or I myself have had problems in the past, if I can sort of show them solutions to those problems, that sort of starts to get them more inside and get them more engaged, and then they start to open up about the issues that they've got, either from the resources that they've got or the knowledge they've got. And then once they have that open communication with us, we can then start really ticking off our solutions and showing the solutions that we have for them.
Are people nervous about talking to you then? I kind of pick up from what you've said.
People are guarded, I would say.
Yeah.
People don't, engineers, I find they can do anything. So, not many, who likes to admit to a failing?
Yeah. I love a good success story, Gareth. Throw one at me, because we like a bit of positivity.
Yeah, so again, going through to a positive success story, we got one of our big customers had multiple sites all around the world. They're all making the same parts, same machines, but they're all coming up with different cycle times, because if you give a part the same part to an engineer, 10 different engineers are going to come up with 10 different ways of manufacturing it. So again, the cost was fluctuating.
They're a stupidly creative bunch, aren't they?
Yes, they are. Everybody
You're not an engineer, are you, Rowan? No.
Everybody thinks their way is the best way.
It is. What do you mean?
Well, this is true. That's what I'm always saying. But so they came to us. They were an Hexagon user, or have been for many years. They came to us with that problem. So we've given them a solution. So basically, as part of Hexagon, you get a product embedded in it called Strategy Manager. So we spoke previously about automatically applying strategies. So in Hexagon, we've written some standard strategies for facing, milling, drilling, as such. With Strategy Manager, this allows you to, or the end user, to say, right, this is how we do it. So you can write your own strategies in the system, so that basically when it sees a feature, it will automatically apply these strategies. Again, it's a very in-depth process, but you can literally, and we've done it now for this customer, where they will literally take in a model. It can be any CAD model. There's loads of fors and whys and what ifs, but that's all built into the strategy. Take in the solid model, press a button, and it will do everything. It will find the features, it will put all the toolpaths on based on what the customer has recommended. It will simulate it, it will spit out the G-code, and they can just do this wherever they are. If they're in China, they're in America, they're in Europe. They all use the same process, and they're all making the same part in the same way, the same cycle time. So again, yeah, it's been really a great project for us to help automate their process.
And that's amazing. You can do the same part in the exact same way in 10 different sites around the world, and those otherwise would be done. You'd have different bore finishes on one place, different ways of making pockets with different fillets or whatever. So it's great that you can standardise this even around the world using one piece of software, which is Hexagon.
I think the word there as well is kind of standardising it, and once you put you removing those variables, and to standardise something makes it all the more powerful because everyone's on the same page as well.
And easy to understand.
Yeah, absolutely.
Yeah,
Definitely. But surely, I mean, we've talked about Esprit, Hexagon, Visi, all the different, every single software it seems you guys offer for production has some form of automation. Is there something we've missed? Is there anything?
Yeah, so again, sheet metal industry as well. So we've got market-leading product Radan, which again, it's been around for nearly 40 years. It's developed by ourselves and still.
And how does that automate? How does it make operators' life easier?
So again, from the sheet metal side, it's the skill shortage is a big thing in that industry because a lot of the experience press brake operators, profile punch users, fabrication side of the sheet metal.
A press brake is a complicated piece of machinery.
Yeah, press brake, but again, you've got all that experience, which is people are beginning to retire and leave the industry, whereas so they're taking all the knowledge of the actual bend allowances, just because you say it needs to be a bend at 90 degrees, but there is a percentage of...
You've got to bend at 92 degrees, haven't you? And it'll spring back.
But also it takes... There's the bend allowance, which again will alter the blank. So again, without this experience, from many years of experience, you can take that into rad bend, for instance. You're taking the 3D model, press the button, it basically flattens the part. It will tell you what the developed length is, so what flat bank you need to start off with, which again then you can feed that back into rad profile, which again will do the lasering profile or the punch profile. So again, that's another thing that's big on the list is obviously expense with material and shortages. So Radan's got the best nesting system on the market. And again, it utilises and matches irregular shapes to get the most utilisation out of your sheet metal. Then you can automatic tool your press brake. Radan rad bend will actually tell you whether you can physically make it or not. It will also look into your tool database and say, actually, you haven't got that tool.
I was going to say, because if I looked at a piece of sheet metal, I would have no idea whether it's bendable or not.
Mm. Yeah, so it works all of that out for you. It'll tell you, yes, you need to buy that tool. No, you don't. And it will also give you a simulation. So again, for helping with the apprentices or somebody who's you're upskilling, they can physically watch the simulation, and it will actually tell them, especially if there's multiple bends, upside, downside, and you've watched the simulation, and it will, like a training aid, you can physically tell you which way to put it in, when to turn it over. So again, that's from the rad bend side, and again, right at the start of the journey, you initially have to quote the product. So with Radan, we got a product called Rad Quote. So again, you can literally take in a customer's drawing, be it a DXF, or you could take in a 3D solid model. Again, that will then unfold that will then put the lasering cost, the punching cost, the bending cost. It works out the gas costs, all the consumables, and then you can add things to it. So if you're putting PEMS inserts in, welding, painting, you can add that to it. So that then gives you the quote from that side. So we've got a solution for all of your sheet metal.
And all of these would previously be done with like Excel spreadsheets, or previous to that would be done with loads of big drafting sheets and calculations. And there's so much human energy and effort that would have gone into what is now completely automatable. And I guess it allows sheet metal companies to spend more time and money on what they're best at, which is making good parts and not worrying about all the more benign stuff, which is just trying to unbend a part. You want to laser cut something, you want to bend it, you want to get it out. You don't want to worry about which tools you need. So it's great that you can leverage this kind of software to improve your business profitability and also efficiency.
I think we're going to have to wrap it up there, gents. So I think everyone's going to probably need a little drink in just a few moments' time. But thank you very much for your time today. It's really interesting. Everyone thinks about automation so much. We said this at the beginning, off, not camera, but, off the podcast, saying, we say automation, everyone thinks of hardware, but this is just a whole new world, which I think sometimes is slightly scarier than going towards the, with the software. So anyway, thank you so much. And thank you very much, everybody, for listening. So do stay in touch with us. If you've got any questions or anything, contact us, MTDCNC, on all of our social channels, and we can forward on any questions or inquiries to the guys here at Hexagon. No trouble at all to do that. So thank you, everyone, each of you, for coming all the way to Northampton to talk to us about all of your products and to educate our listeners with all of your industry knowledge. We hope you've all enjoyed it. Do subscribe to the channel, and we look forward to having you listening to us again in the future. Thank you again.
Thanks for listening to the MTD podcast. If you found value in this episode, please subscribe and leave a rating and review. Find more episodes on mtdcnc.com.